Now that we know about the central limit theorem, we can start our very first statistical test. We're going to use what we know about sampling distributions, and the standard error to start into inferential statistics.
For example, if a sample is drawn from a population, the sample mean is our best estimate of what the population mean is for that variable. With sampling distributions, you draw an infinite number of samples. Whenever you truly do a study, you only draw a single sample and you have one estimate of the mean.
We know that that estimate is not always going to be exactly what the population mean is. It could be a little bit higher or a little bit lower than the population mean.
So what we'll do is we're going to calculate a confidence interval around our sample mean and see if it captures the population mean. And in fact, we can actually put a level of confidence around how likely it is that our confidence interval captures the population mean.
Here's the equation that we would use to do that. Notice we take our sample mean, and from that we subtract and add to it value, and that value is a z-score times the standard error of the mean. The z-score we choose will determine our level of confidence.
In other words, we simply add and subtract from the sample mean a value that is dependent upon how variable the standard error is and how confident we want to be of our decision.
Here again, the z-value that we select will determine how much confidence we can have that the population mean is actually in the range of our interval.
Two commonly used values for the confidence interval are the 95th and the 99% confidence. And the numbers that you see, 1.96, that's the z-score associated with 95%. Remember, we used two standard deviations plus and minus the mean encompasses about 95% of the scores. If you wanted to get 99% of the scores, you'd go up and down 2.58 standard deviations. You multiply those values times the standard error and then add and subtract it from the mean to develop a confidence interval.
So here's an example. Let's say that we measured the resting heart rate for a sample of 16 12-year-old boys, and we got a mean of 77. Our best estimate of the population mean now is 77.
Remember, we only drew one sample, and our best estimate of the mean is what we've drawn from that sample.
However, from published data, we know that the mean for 12-year-old boys is 80, and the standard deviation is 6.5.
Notice we've reflected the mean as mu for the population, and the standard deviation for the population, 6.5, is sigma.
So to calculate the standard error of the mean, we divide 6.5 by the square root of our n, which is 16, so the standard error is equal to 1.625.
So then you calculate the 95% confidence interval by using the formula previously. It's the mean minus the z times the standard error of the mean, to the mean plus 1.96 times the standard error of the mean. When we do that, we find that the 95% confidence interval on our value of 77 ranges from 73.815 to 80.185.
So now we can use this confidence interval to come to the conclusion that the mean resting heart rate of our sample, 77, is not different than the national mean of 80 because 80 lies inside of our confidence interval.
Here's an illustration that shows you that. The mean for our sample was 77. The mean of the population is 80. Note the 95% confidence interval ranges from 73.815 to 80.185, and the value of 80 lies within that confidence interval. So we have to assume that our 77 is a likely observation when the true mean is 80.